happening? It was falling down because of gravity. And the reason it went up in the air was because it had some initial velocity. Okay, so we're going to take that initial velocity and we're going to take the fact that gravity is pulling on it to come up with vectors and for velocity and position. So,
Yes. Sorry, I have something else.
okay. So I shoot the projectile up in the air with initial velocity. As soon as it released from the gun, gravity starts pulling on it. And it does.
What is so funny?
No, sorry.
I really nothing. He was sick.
Okay. And gravity pulls on it and it produces it to come down. So, what is the initial velocity? The initial velocity has a x component and a y component. The x component would be what I can write down. Which one am I looking at, Emma? Okay. All right. What is x? X is equal to. Think of that as sine. Think of the angle as theta. So the cosine of theta would be x over v sub naught, the magnitude of v sub naught. So x is equal to the magnitude of v sub naught times the cosine of theta. So the x component is the magnitude of v times the cosine of theta times I. That's the initial velocity. And the y component would be the magnitude of v times sine of theta. Okay. Now, as soon as it releases the gun, what happens? Gravity starts working on it. And so force is mass times acceleration. And acceleration can be written as the second derivative of its position. Okay? And what is acceleration? It is gravity. So this is basically equal to negative m times g in the j direction. Okay. So the second derivative of its position is equal to minus gj. Now let's solve for velocity. How would we solve for velocity? G, that's gravity. Gravity. So how do we solve for velocity? Well, this is acceleration, which would be the rate of change of velocity, which is acceleration. So how can we solve for velocity? Integrate. So we go dv equals minus gj dt. And so the velocity vector is going to be what? Integrate g with respect to t. Negative g times t. Okay? Negative g times t, j, plus what?
Plus c.
Plus an initial velocity. Okay? So what is the velocity vector? The velocity vector is the initial velocity, which is this, plus the minus gravity times time, j vector. So the x component would be v sub naught cosine of theta times I plus v sub naught sine of theta j minus gt j. Okay? So that's your velocity vector. Now let's just use this simple one here to get our next stage. So your velocity vector is the rate of change of its position vector, which is equal to minus gtj plus initial velocity. So now we want to solve for r, its position vector. So what do? We integrate this, so dr equals minus gtj plus v sub naught dt. So r is going to be what? The r vector is going to be
dt squared over 2.
T squared minus g over 2, or basically 1/2, right? 1/2 gt squared j plus v sub naught t plus initial position, which we'll call r sub naught. Yes?
Is GT in parentheses or is it T squared?
GT.
T is squared.
The t is being squared. Because you're just raising t to the second power, and the g is a constant in front of it.
Okay.
Okay? So now, what is our position vector? Our position vector is our initial velocity vector plus the initial position plus this. So v sub naught t would be this thing with the t times it. Okay? So it would be minus 1/2 gt squared j plus v magnitude of v cosine of theta I plus magnitude of v sine of theta j all times t plus r sub naught. Okay, so if you follow that, r sub naught is the beginning part vector. I'm holding the gun above the ground, so r sub naught would be 3 feet above the ground, 0 distance over.
Why isn't GT? Or no, wait.
Okay, I went dr dt, I brought the dt over, and I integrate. So you integrate this, and it's
Maybe the first part, but I think it's VOT. Or V sub
because
naught.
v sub naught times t, because you're integrating a constant v sub naught
Yeah, yeah.
times t.
Yeah.
There's not one number.
Okay, this gets messy, so we gotta at least be quiet so people can hear.
And so R sub naught is basically V.
Yes, that's a constant. Okay, so now let's put this thing, everything times I,
Wait,
and
what does
everything
this
times
equation mean?
Huh?
What does this even mean?
This is the vector equation. This is, if I shot this thing out, there is R, vector R, after a certain time period. There is the vector at another time period. It's following the path of the projectile.
That is so helpful, thank you.
Okay?
That makes so much more sense.
The v is the velocity that this projectile has at each of these moments. That would be the v.
Do you go over that?
What's that?
I like the last one.
All right. It's going from here to here? Which part?
That, how you went from, no, the one below is,
The-
yeah, that
Here
one.
to here.
Yeah,
All right, I get this by taking the integral of this.
yeah, okay.
So that's t squared over 2 times g.
Yeah.
And this is just v sub naught times t.
Yeah.
Plus a constant, which is the beginning part,
Yeah.
r sub naught.
No, like how you went to the cosine.
Okay, so then, what is v sub naught? That's the initial velocity. The initial velocity was this right here, that we created at the beginning. So I took this and put it in for the v sub naught.
Okay.
Okay? Now, I have a question.
What's the R?
That's its position. Its position vector. So, at any moment, that's r sitting out here. It tells you where it is at every second. All right. Now let's put everything together. This is times I. Times t. You guys, this times t gives you the I part. And then the j part would be the v sub naught sine of theta times t minus the 1/2 g t squared times j. And then I'll just put the r sub naught out here. So we don't know what components are in that yet. And for this particular one, r sub naught is going to be 0. Because our example up here, I'm going to pretend as if I had the gun right at the ground level. Okay. So this is the formula that is r, the position vector. It tells you where that projectile is at any moment, based on the angle, based on the velocity, and based on the time that you'd be in the air. Okay? So this is the x component. The x component of the vector is this. And the y component is this. Okay? Yes?
Would this equation be using like anti-area on your thing? Would it be in computer systems with anti-area businesses?
I'm sure something that I can't see correctly. I mean, the principle here is all we're using is the initial velocity and gravity. We're not indicating any way air currents or any other acceleration or deceleration. It's just something being shot out at a certain angle, a certain speed, and then gravity is applying. So that would be the formula that would give its position. So let's do an example. All right, let's wait. Let's settle down. Thank you. All right, here's an example. Let's say the angle is 60 degrees. Let's say your velocity that you shoot it out at is 500 feet per second. What is its position in 10 seconds? So all you have to do to find its position is use these two equations. So its x position is going to be 500 feet times the cosine of 60 degrees times 10 seconds. Okay. And if you do that, it's at 2,500 feet. So at this point here, that's 2,500 feet out. What? Pardon me?
Feet. Sorry. There's too many things that do
Zero.
the same thing.
The truth.
Okay.
It's actually 16.
The y value is the initial velocity, initial speed. Okay, I shouldn't put 500 there. Sorry. 500 feet per second times the sine of 60 times 10 seconds minus 1/2 32. Do you know what 32 is? Gravity in feet per second times 10 squared. So I'm simply taking the numbers, plugging it into here. And if we work that out, it comes out to be 2,730 feet. So its height at that point would be 2,730 feet. It's out 2,500 feet at a height of 2,730 feet. Okay.
Or any other unit. Miles.
Okay, any questions so far? There's one. All right.
No more. I already have the
Okay. Okay, find its maximum height. All right, when is it going to reach its maximum height? When the y, not the y is 0, but the rate of change of y. So when dy dt is 0, when this thing goes up and doesn't go up anymore and starts coming down, when that's 0, that's when its max is going to be. So take your y component, find dy dt. So we're taking the derivative of this. Well, that's pretty easy. Derivative of this with respect to time would be v sub naught, magnitude of v sub naught sine of theta times 1 minus 2 over 1/2 gt. So basically it would be v sub naught sine of theta minus gt. We haven't got it yet. We're just... Okay. This projectile is going up in the air. It's got a horizontal component and a vertical component. It's going to reach its maximum height when its vertical component stops going up and starts coming down. And that's when the rate of change of y is 0. So first of all, we're finding the rate of change of y. Did I goof?
Cosine?
Oh. No, we're doing this.
But if you took the derivative of sine, but it's a set variable though. Oh,
The theta is constant. The only thing that's changing is time.
Yeah, whatever.
The only thing that's changing is time. So, good question? Okay. So now, hello. This is the rate of change of y. When is it going to be at its maximum value, or the maximum height? When the derivative is 0. So set this equal to 0 and solve for t. So the magnitude times the sine of theta equals gt. So your maximum height is going to occur when the magnitude times the sine of theta divided by g. So that's when the maximum height will occur. Okay? What is the maximum height? Y max, maximum height, would be this formula, but what do we put for t? We put the formula we just solved for. So we put the magnitude of v times sine of theta times t, which is this. So magnitude of v sine of theta over g minus 1/2 gt squared. Minus 1/2 g t squared, which would be v sub naught sine of theta over g squared. So I simply took this result, plugged it in for t over here. You will have a formula sheet on the test.
Wait, seriously?
Oh, God.
On this test or on the AP test?
On this test.
Oh, not on the,
Well, you did the formulas on the AP test.
Could we see the AP formula sheet like sooner rather than later so we know what we need to know?
Okay, so this now becomes what? This is v sub naught sine of theta to v sub naught sine of theta, so it's v sub naught sine of theta squared over g. And this becomes minus v sub naught sine of theta squared on top. And we're going to have a g squared on the bottom and a g on the top, so what happens to one of the g's? One of the g's cancel, and we have a 2 there, so we have 2g.
And then you just plug in numbers?
Well, let's get a common denominator here. Common denominator is
2.
2g, so just multiply top and bottom by 2. So we have 2 of these squared minus 1 of these squared over 2g gives you 1 of them over 2g. So v sub naught sine of theta squared over 2g. That's the maximum height. So, how high is it going to go? You plug in the speed, you plug in the angle, square the results, the sine of that angle squared, divided by 2g, and you have your maximum height formula. Yes?
On that bottom left equation, y max,
Yep.
another g after the 1/2. What happened to that?
This is g.
Would it cancel out with the other g?
Yeah, but this g is being squared.
Oh, okay.
That's why we still have a g on the bottom. All right.
I can't believe we lost so much less.
Okay. Okay. When will the projectile land? When will the projectile land? When y equals 0. So here's your equation for y. So set that equal to 0. How do we solve that?
Who knows?
Solving for t. First thing you do is factor out a t, because there's 2 t's in there. So now you only get that equation. Obviously, when t is 0, the projectile is going to be on the ground. But it's also going to be on the ground when this occurs. So v sub naught sine of theta equals 1/2 gt. So solve for t. So multiply both sides by 2. 2 times the velocity, sine of theta, divided by g, equals t. So this is basically the time in the air. Because when it lands, it's going to be in the air. Okay. All right, so now we've got the maximum height time, the maximum height. Actually, notice notice the correlation between this one and this one.
It's twice it.
Because it started on the ground, went up in a nice parabola, and came down the ground, so it would be twice as much. Okay, final thing. Where does it land?
In a bush.
Okay? It's going to land when the time in the air is expired. We have a formula for time in air. So where do we plug that into? Into the x equation. So the time in the air, or the landing point, would be x equals this formula times the time it's in the air. So you plug that formula in. X equals initial velocity, cosine of theta, times t. And this is what we established to be t. So 2 times the initial velocity, sine of theta, over g. I'm using the front board, Francis. If I run out of room, I'll go back there and use that. Okay, so this becomes the initial velocity squared times 2 times the sine of theta times the cosine of theta, all over g. Okay, pre-calc people, what's the identity for 2 sine of theta cosine theta?
That's what they want.
It's the sine of 2 theta. Sine of 2 theta.
Hey, that's what I said.
That's why it's very.
So where does the projectile land? Whatever the velocity is squared times the sine of twice the angle divided by gravity. All right, now, when you have a sine function, the sine function can never, its largest the sine can ever be is 1. And when is it going to be 1? When the angle is pi over 2, right? 90 degrees? That's when your sine is the largest? Okay, if the angle is, theta is pi over 2, So you want this to be pi over 2, because that would give you your maximum value for sine. All right? So what would theta have to be? Pi over 4. So for max value of sine, theta must equal pi over 4. Because then that would produce a pi over 2, which would give you the largest value for that expression. And of course, what's pi over 4? In degrees. 45 degrees. So the projectile, all things being equal, should be 45 degrees to get your maximum distance. Wouldn't get you your maximum height necessarily, but it gets you maximum distance. Alright, so this is distance. This is the maximum height. This is the maximum height time. And this is the time in the air. You will be given those formulas on the test. Yeah. But I think it was good to see us get them rather than just give them. All right, tomorrow, then we'll make use of these formulas to actually come up with some couple practical situations. One where you hit a baseball and we calculate whether it's really a home run or not. And the other is taken from the Olympics, in the 1994 Olympics. All right. What's that? Okay, so I'm on 10.4. Where are you guys?
10.2.
10.2.
10.0.
Okay.